Hello and welcome to our first lesson in Foundations of Math 1. Today we are starting out learning about our real number system and the properties of the real number system. And so we're just going to jump right in with how do we categorize numbers. Okay, so we're going to start out with the least specific thing possible, real numbers. The symbol for real numbers is a capital R. And this is all numbers. So I might say this is all humans. Okay, everyone would fit this category, and all numbers fit this category that we will learn about in Math 1. Next, let's break it down a little bit. You are either going to be rational or you're going to be irrational. So that might be similar to being I'm a boy or I'm a girl. So we're all human. Some of us are boys, some of us are girls. Irrational numbers, the symbol for that is a capital I. And some examples would be pi. Why is pi an example? Pi is a decimal that never ends, and that is what it says right there in the description of irrational. Another one would be square root of 2. Okay, it has a decimal that never ends, but it also does not have a repeating pattern. So if I had like 0.33333 forever, that would be a repeating pattern, and that would fit into the rational numbers over here. Okay, and then another option would be a mumbo jumbo number, numbers that are difficult to really make good sense of, decimals that go on forever and have no repeating pattern. So there's 3 good examples. The other option would be if you're rational. The symbol for rational is the capital Q. Okay, these are numbers that can be expressed as fractions. So 0.3 repeating can also be expressed as 1/3. Okay, decimals that end, so like negative 0.67, it has a definitive stopping point. Okay, or numbers like that. The square root of 16, that actually simplifies to just equal 4. And so that still qualifies as a rational number. Now let's look more closely at our rational numbers. If you have a number and you decide that it's irrational, that is the stopping point right there. You can't classify it any further, okay? It's just done right there. But if you end up having a rational number, then you can continue to classify it further. So if you're a rational number, you're going to check and see, are you an integer? Integers are, let's draw a number line here. Integers are your positive, so that's 0 in the middle, positive and negative numbers in both directions, okay? But it includes, so negative and positive, but there are no fractions and no decimals. No decimals. Okay. As I fill in my notes, you should be following along with me and filling in your notes exactly the same way that I'm doing mine. Okay, this will ensure that you get a good notebook grade at the end of the quarter. Let's talk about whole numbers now. And I'm going to create another number line, and you should be doing the same thing. But the difference here is that my number line is not going to continue in both directions. Whole numbers, they start at the number 0, and they only get larger. So it might be 1, it might be 2, it might be 5, it might be 12, it might be 200, okay? But it is all positive numbers. Again, it should not include fractions and it should not include decimals. Okay. Our natural numbers. So that is a capital N. Our natural numbers are going to be our counting numbers, but it does not include 0. So if you think about it, when a child is first learning how to count, they would start with the number 1. They do not start at 0. Okay? And I'm going to carry this down again. No fractions and no decimals in our natural numbers. What I'd like for you to do now is look at numbers 1, 2, 3, and 4 in the examples down below on your paper. Pause this video and work on those 4 problems. Okay, at this point you should have completed at least those first 3 problems before hitting unpause on the video. So let's go on to the next page and take a look at what you've done, okay? The number 30, I'm going to continue referring to this chart here to help me, okay? Every single number that we discuss will always be a real number. So honestly, what you can do right now is go ahead and put an R in every single box, because that is what we are learning about in foundations. Okay, everything is a rational number. I'm sorry, everything is a real number. Next, we need to look at, are they decimals or are they not decimals? Okay, if they're not a decimal at all, then we know automatically that they are in the rational number system, and they're either going to be an integer, a whole number, or natural number. But you want to check each one off as you go through. So the number 30, it's real. It is not a decimal and not a fraction, so it's definitely rational. It is a positive number, so it is an integer as well as a whole number. And it is not negative, so, and it's not just 0, so it's also a natural number. It's everything except for irrational, okay? You can only be rational or irrational. Keep that in mind. And I have actually already completed 1 through 5. Now, I did add a note up here in blue that whenever you see something that can be reduced, you need to reduce it before you can classify it. So looking at number 6, negative square roots of 9, that does reduce to a negative 3. 6 divided by 3 in number 7, that's the same as 2. And I added this note down here in number 9, 5.3 with a bar on top. That bar means 0.333333, and that is going to continue forever, okay? And finally, in number 10, the square root of 144 is 12. The square root of negative 3 is 3. So I want you to go ahead and pause this video again and continue classifying the remaining problems. Now that you have completed your 12 questions, I want you to go ahead and check your answers. And if there's anything that you're still not fully understanding, you should raise your hand and ask Ms. Brown to come assist you. If you do have a pretty good understanding of how to classify these numbers, I want you to continue along with the video. We are now going to continue on and talk about our properties of real numbers and how do we work with these numbers. What are some basic rules for working with them? Okay. The first rule that we've got is called the commutative property. This is for addition or subtraction. And if you look through all of these are all addition or multiplication. Okay. My commutative property means that the order that I put my numbers or variables in does not matter. And so I am going to come up here and we're going to do an example of addition. Okay, what that means is 2 plus 3 is the same as 3 plus 2. Or if I'm going to use algebra, 2 plus a, an unknown variable, is the same as a plus 2. Okay? Let's do an example with multiplication. Multiplication. So go ahead and make sure that you're doing your notes correctly, just as I am. If you would like to color code with me, color pencils are a great addition to your note, your note supplies. Okay. Also, color pens work as well. So for multiplication, an example would be 2 times 5. 2 times 5 is 10, which is exactly the same as 5 times 2. I can also do this with variables. Okay, x times y is the same as y times x. If you have a question about the commutative property, stop this video and ask Miss Brown. Otherwise, we're going to go ahead and move on to grouping. Okay, the associative property means that the way that we group our variables or letters, as long as we are adding or multiplying them, does not matter. So let's do an addition example. I'm going to shorthand the word addition here. If I have 1 plus 2 parentheses plus 3, that is going to give me the same result if I did 1 plus and then grouped the 2 and 3 together. Okay. My multiplicative or multiplication example, let's go with mult for that to shorthand it. If I did 1 times 2 and got 2 and times that by 3, I'd get 6. Well, what if I did 1 times 2 times 3 instead? 2 times 3 is 6. 6 times 1 is still 6. So it's going to work for me either way. And lastly is my identity property. The identity property is what can you add to a number or what can you multiply to a number so that it will stay the same. Okay, so let's do addition first. If I have the number 2, what can I do to that number 2 so that the result will still be 2? And again, this is addition, so we're going to need to have a plus sign there. What do you add to 2 so it doesn't change the value? And while you're thinking about that, let's do multiplication. If I had 2 times something, what would I multiply it by so I do not change its value? Well, the answers here for adding 2 plus 0 will keep you at 2, or 2 times 1 will keep you at 2. Okay, so the additive identity for obviously addition, additive identity is 0. And then the multiplicative identity is 1. Okay, let's go on and see a few more properties that you still have on your page, starting with the inverse property. The inverse property, another word for inverse, is opposite. Okay, so for adding, what could I add to the number -4 to make it equal 0? Okay, or to cancel it out. For multiplication, I'm asking myself, if I had -4, what would I multiply it by to equal 1? Because there is no number that would be an opposite that you can multiply to get 0. If you think about multiplication, the only way to get to 0 is to multiply by 0. So the opposite of 0 is 0. Any other numbers, they have to have a different opposite. It can't be 0 when it comes to multiplication. Okay, so what we're going to have for our multiplication is -4 plus a +4, that would equal 0. Okay, inversely, if I had a 4, if I were to add a number to that to equal 0, I would have to add a -4 to it. All right? So +4 and -4 are inverses. What about multiplication, though? That's a little bit harder. What is the opposite of multiplication? I want you to think of that. It is division, okay? So whatever it is that I do, I need to divide by a -4. Well, I'm just going to pop a 1 up there for a placeholder, and that is going to be the multiplicative inverse, okay? Instead of multiplying by -4, you divide by that -4. Let's move on to the zero product property, which is very simple. It says multiplying by 0 always equals 0. So if I have 17 times 0, x times 0, -1023 times 0, it doesn't matter. Every one of those examples, the answer is 0. And finally, on this side of my paper, we're going to do the distributive property. So if I were to write an example up here first, 2 times x plus 1, and I asked you, what do I do to solve this problem? Most of you would know right away that I need to multiply a value. So I'm going to multiply this value that's on the outside to everything that is on the inside of the parentheses. Okay, so if you want to write that word also, parentheses. So to show my work, I'm going to do 2 times x is 2x. Change colors. 2 times 1 is a positive 2. And that's my answer. If you have any questions about any of the properties on this page, I need you to pause your video and ask Ms. Brown for clarification. If you're ready to finish up with some new properties that you have not learned in 8th grade, let's go ahead and go on to our next page. Okay, so new to Math 1, or our intro to Math 1, is going to be our reflexive property, our symmetric property, and our transitive property. And I'm going to go ahead and fill in each one of those for you. Our first property is the reflexive property, and it says that a value is always going to be equal to itself. Okay, so 16 does indeed equal 16. 2a is going to be the same as 2a. And then if we start discussing exponents even, 4x squared equals 4x squared. Okay. The symmetric property, let's see what it says. The symmetric property states if a equals b, then b equals a. So let's look at an example. If x equals 3, then we can also say that 3 equals x. It's just writing it in the reverse order, which we're going to use a lot when we're solving equations if we end up with our variable term on the right-hand side like we did right there. Okay? All right. You can also use it before the variable is completely isolated. So if I have 6 equals 2x, then I can say 2x equals 6, and that just helps me get my variable back onto the left. And finally, my transitive property states that if a equals b and b equals c, then a must also equal c. And I think an example of this makes it a lot easier to see, okay? So here's my example. If 4 plus 3 equals 7, so I want you to keep in mind this is A and this is going to be B, okay? If 4 plus 3 equals 7 and 7 equals 5 plus 2, which is also a true statement. So 7 here is the B. 5 plus 2 is something totally new, so we're going to call that C. Then I can say, and I'm going to run out of room here, 4 plus 3 equals 5 plus 2. And it is true. 4 plus 3 is 7. 5 plus 2 is 7. And I do know for absolute certainty 7 equals 7. Okay? We learned that back when we were talking about every number being equal to itself. Okay? Alrighty. Let's move on to probably the hardest property today. It is the closure property. Okay? When we're talking about sets of numbers, and when I say sets of numbers, I'm talking about the set of the real numbers, or the set of the integers, or the set of the natural counting numbers. Okay, that's what I mean by set. If they are closed under multiplication, addition, subtraction, division, okay, the 4 different operations. If it's true, we can just say true. If it's false, we need to give an example that proves it's false. Okay? So let's look at this. Integers are closed under multiplication. So integers include negative and positive numbers. So if I have a negative 2 times a negative 2, I get a positive 4, but positive 4 is still an integer. And I have countless examples where that will always come out true. Let's talk about the natural numbers. Are the natural numbers closed under subtraction? So remember, natural numbers are 0, 1, 2. No, I'm sorry, they're not. They do not include 0. Okay? So let's come up with 2 natural numbers that I can subtract. What if I did 2 minus 2? That now equals 0. 2 was a natural number, and then 2 was a natural number. When I subtracted them, this is not a natural number anymore. It is now a whole number. Okay? So that is false, because that came out to be a whole number. Are even numbers closed under addition? So if I add 2 even numbers together, will I always come out with an even number? I think most of us would think that is true, and it is. Okay. Irrational numbers, are they closed under division? So if I take 2 rational numbers and divide them, will I still end up with a rational number? And this one might be a little harder for you because we're still getting used to irrational numbers. I'm going to come up with an example, an easy example for you. We know that pi is irrational. And if you think about another irrational number that we could divide it by, how about pi again? What is anything divided by itself going to give you? And the answer is 1. It doesn't matter how crazy it looks. Okay, 1 is not irrational. 1 falls in the natural numbers, the whole numbers, the integers, the rationals. It falls into everything. Okay, so this one is false. And then perfect squares. We're going to make a little table or chart out to the side here. A lot of people forget those perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, so on and so forth. It is just a number that is being multiplied by itself. Okay, and 7 squared is 49. I'm going to kind of stop there, even though it does continue on, and it's good to know your perfect squares, at least up to 12 or 13. Okay, our perfect squares closed under subtraction. So I'm going to pick 2 of these perfect squares, and I'm going to subtract them. 16 minus 9. I'm going to take those. What is 16 minus 9? Okay, gave you a second to think about it. I get 7. Is 7 anywhere on this list? 1, 4, 9, 16, 25. It's really not. 7 falls in between the 4 and the 9, which means that it is not a number that will give me a perfect square. Okay? It is not one of those perfect squares. So that is closure. Closure might be a little more difficult to think about, but I want you to always refer to examples for yourself. All right? That is the end of our lesson number 1 notes. At this point, you should have your entire notes work completely filled in. If not, I want you to go back, rewatch this video, and fill in your notes. When you are done with your notes, you may begin working on your practice assignment, which is on quizzes. All right, thank you so much. Hope this helps.